Now we're going to talk about how you find the capacitance of a circuit that has multiple capacitors in it. It turns out the overall circuit behaves like there's an equivalent capacitance, as if we took all the capacitors in the circuit, replaced them with just one specific capacitor of a specific value, okay? Which is handy because it means you can make a lot of different capacitances with a bunch of very standard capacitors. You don't need to have every possible capacitor value in your supply cabinet. The first case I want to discuss is the parallel case. Okay, what makes this parallel is that the current, if you like, goes down the wires and then goes two different directions parallel to each other. Okay? Now in a real circuit they don't actually have to be physically parallel. It just means there's a branch and things go down and then they meet up at the other side. If that happens, the net equivalent capacitance goes like the sum of all the capacitors that are in parallel at that point. Okay? We could keep doing this for a very long time. You expect this in this case because we've effectively just taken this capacitor and this capacitor. The areas of these plates have basically both increased. They have the same voltage across them because it's the same as the voltage over here, but we've just made twice the area, or however much more area, for the two of them. So that's a pretty straightforward calculation. Let's try the case of a series capacitor. Series means we hit one, then we hit the other, one after the other, in series if you like. Here's where it gets a lot more interesting. The equivalent capacitance goes like, well, this is where it gets weird. We actually find 1 over the equivalent capacitance. That's actually 1 over C1 plus 1 over C2 plus ... Keep going 1 overs like that, okay? The reason why I'm not going to really flesh out, it's actually not that hard mathematically to show. It turns out that both of these plates get the same charge, plus and minus. This one must get the same plus Q as this one does, because the negative charges that went there left behind the positive charges here, and then vice versa. So they all have the same charge, but instead of having the same voltage, capital V, over here, this is split up between them, okay, in a way that has to add up to V. And if you go back and look at the definition of capacitance, that implies you have to add them in reciprocal. So let's do a quick calculation. Let's imagine, I don't know, a 1 microfarad capacitor. A 1 farad capacitor is huge, and a 2 microfarad capacitor. And let's ask, what's the C in series, and what's the C in parallel? Okay. Well, which one's easy to do first? The parallel is easiest to do first because it's just the sum. It's 1 microfarad plus 2 microfarads equals 3 microfarads. Easy peasy. The one in series I've actually got to do in reciprocal. So I like to write it like 1 over. And I do 1 over 1 microfarad plus 1 over 2 microfarads. Well, this is 1 times 10 to the 6th, 1 over farads. And this is 1/2 times 10 to the 6th farads. Or if you prefer 1 over microfarads plus 1/2 1 over microfarads. That's 1.5 1 over microfarads. Okay? But that's 1 over C series. So C series must be 1 over all of this. Well, 1 over 1.5 is about 2/3, so it's about 0.67 microfarads. Okay? That's not too bad. It's fairly easy to calculate these. I like to just add up the reciprocals first and then take the reciprocal of whatever I get at the end. Okay? The reciprocal button on your calculator will be hugely helpful for this, by the way. If you don't know where it is, and you don't know where it is in the pink calculators, now's a good time to find out. It's right over the 7 key on the pink calculators if you're looking there. I don't know where it is on your calculator, of course. Okay, next video will be about what capacitors are good for. And the answer is not absolutely nothing. Good God, y'all.